So in my previous posts, I looked at performing tree traversal of an XML document using both a breadth-first and a depth-first approach. Now, in the previous posts, the logic for traversing the tree was tightly coupled and commingled with the logic of consuming each individual node, which means that the traversal logic itself couldn't be reused because it was, again, coupled to the logic around the node consumption. So in this follow-up post, what I wanted to do was look at a way we can use a ColdFusion Closure to separate the traversal logic from the individual node consumption logic, thereby making the traversal logic reusable in a variety of contexts. And just as before, we have our XML document here that has nodes that have letters and numbers. The letter represents the depth of the node within the tree, and then the numbers indicate the breadth of the node within a particular level. So after we define our tree, we're going to call this WalkTree method, and we're going to pass in the XML document, and then you'll see that as a second argument here, we're passing in a ColdFusion Closure. And the closure accepts a node, and what's going to happen is that the WalkTree function is going to iterate over this tree using a depth-first algorithm, and then for each node that it visits, it's going to invoke this callback, passing in the node so that we can echo out the name of the node, and then we're just going to dump out the tree here. So before we look at that, let's just go ahead and run this so we get a sense of what's happening. Here we can see that all of the XML node names were echoed along the top, and we can see by the numbers, A1, B1, C1, D1, D2, that we're iterating using that depth-first approach, right? A1, B1, C1, D1, D2, right? That's exactly what we're seeing here. So we're seeing that the depth-first algorithm is working, and we're also seeing that our callback here is successfully getting called for each node, echoing out the XML name of the node. And again, that's what we're seeing along the top. So let's take a look at WalkTree to see what it's doing. WalkTree, again, taking the XML document, taking our closure here, and just as with the previous algorithms, we're using a queue internally to execute the quote-unquote recursive nature of the tree traversal without actually performing recursion. That way we don't have to create a deep call stack. Essentially our call stack is very shallow. All we're doing is sort of pushing and popping, or I should say pushing and shifting items onto and off of this queue respectively, and then for each node that we come across, we invoke that callback and pass in the node. So you can see here that the WalkTree function deals only with the iteration of the tree structure itself, doesn't know anything about how the nodes are being consumed. It's passing each node off to the callback, where the callback is completely encapsulating the logic of the node consumption. So the WalkTree method is encapsulating the tree traversal algorithm, wherein the closure is encapsulating the node consumption algorithm, which again means that we can now reuse this WalkTree function in a variety of different contexts where we want to consume an XML document, but we can then create the specifics of that particular context using this passed-in closure. Now, this is awesome, but every time I convert from an inline approach to a callback-based approach, the very next thought I have is this going to hurt performance? Now, I'll caveat that that's a silly thought to have, because what we want to do is create flexible, reusable, easy-to-maintain code like this and not worry about hyper-optimizing or prematurely optimizing algorithms. But since this is an experiment, we might as well experiment with some speed. So what I did was, again, taking this XML structure, I am creating a simplistic test harness on my local development environment, which means that it means absolutely nothing, right? This is not a production environment. It's not under production load. It's in a very controlled situation. Take it with a grain of salt, but I think, it gives us sort of an order of magnitude type understanding of the performance. So I'm going to run 10 tests, and with each test, I'm going to run 1,000 iterations of both an inline test and a closure-based test. So here's our 10 test count, and then you'll see for each test count, we're going to do an inline test and a callback-based test, right? And each one of these tests calls the WalkTree. This one just passes in the tree because it's going to defer to the WalkTree function to do an inline consumption. This one calls WalkTree, but also passes in a closure. And you can see we're just outputting the name of the XML node to the system output. And then we're just dumping the duration of each one of these tests to the screen. And this WalkTree is exactly like the other function that we just saw. The difference here is that the callback is optional. If it's null, I'm performing the inline test to call system output. However, if the callback is provided, then I'm invoking the callback and passing in the nodes. This would be the inline test versus the callback test. So let's jump into the browser and let's refresh this. And I'll pause the video here because this takes like 30 seconds to run. Okay, and the test has completed, and we can see we have our 10 iterations here, each with 1,000 inline checks and 1,000 callback checks. And what we can see is that in at least some of these cases, like this one, 1150 versus 1413, the callback actually completed faster than the inline, right? So let's just see. So we have this one. They're all pretty close. This one's 6 milliseconds off. This one's faster, 1199 versus 1349. This one's pretty close. All right, so in only 2 of the cases did the callback complete faster, but we can see that in each one of these cases, the timing between the inline test and the callback test are basically neck and neck. So the takeaway here for me, at least, is roughly speaking, the inline consumption and the callback consumption are the same level of performance, meaning that we don't have to worry about the cost of overhead of creating a callback-based algorithm. We can get all that benefit of the reusability and the flexibility of the tree traversal without having to be concerned that it's actually going to have any kind of real performance impact. Again, this is on a local development environment under no production load, but you know, I'm recording this video. I have all my background processes running, and this is running on top of all that. So you know, it's not nothing, but it's also, you know, again, take it with a grain of salt. But just for peace of mind, we can see that we can still create flexible algorithms without worrying too much about the speed.